In this example, we deal with shaft, and gears are located. We say total structure is assembly of a powertrain. In the powertrain, mainly some power is transmitted to this gear and delivered to next stage or next connected gears. Our problem is to find change of angle phi BC here in this, and phi CD. That's the final. Based on the change of angle in this shaft, and finally we would like to know phi BD. What's the change of in this area? And another problem related to this question is please find shear stress BC here, BC, and CD, BD, CD, okay, CD here, this one. We would like to know that. Of course, we know the torque T1, T2 450, T2, T3 is given, and the shaft characteristics is also given. Shear modulus of elasticity is 80 gigapascal is given. Firstly, let's think about free body diagram of this shaft and gears. When I draw it again, this one is shaft. Let's say left hand side, right hand side, let's say E. In between here, we have transmission gears. 1, 2, 3. It's located like this one. Okay. Let's say this point is B, C, D. B, C, D is given like this one. When I draw free body diagram related to torque. When you use right hand rule, T1 is located like this one. T1. T2 is, this one is T1. T2, this direction, T2. And T3, another direction, right hand side, this direction, let's say. Of course, acting point is here, there, and there. Then we have very simple schematics related to power transmission, powertrain. Okay, now let's think about equilibrium. Let's say this direction is positive. Then T1 minus T2, this one is T3, plus T3 equals 0. T1, T2, T3 equals 0. And when you substitute everything, then we know that. And next one, when you cut somewhere here off, then it's like this one. You can draw a free body diagram like this one. This one is T1, and let's say another one. Let's say this one is T, BC, let's say. When you draw here, when you cut here off, then you can draw this kind of free body diagram. Then we can say T1, equals maybe TBC. Of course, direction is another direction compared to T1. And next one, when you cut here, let's say here something TCD. Then with the same method, similarly, when you calculate this direction is positive T1 minus T2, and we introduce the which is acting TCD minus TCD equals 0. Okay, then finally TBC equals TBC. This one equals T1. T1 is 275 Newton meter. And here TCD equals T1 minus T2. T1 minus T2. T1 minus T2. And 250 and 125. 275 minus 450. Then this one is 450, 150 plus 175 Newton meter. 175. Okay, Newton meter. Of course, direction is minus direction. Not this direction, another direction. In reality, in this direction is okay, based on final calculation like this one. Okay, we found TBC and TCD. Based on this value, we can calculate tau BC. Tau BC equals IP, polar moment of inertia, and tau BC, TBC, TR. IP equals polar moment of inertia. That is IP, in this case, 5 over 32 D exponential 4. This one is polar moment of inertia. And next one, tau CD equals same as the case of BC, tau polar moment of inertia, and TCD and radius R. Then you can find TBC, tau BC shear stress, and CD between here. We can find it. Next one, our goal is to find this value, phi BD. Phi BD equals phi CD plus phi BC. When you add up, then finally you can calculate phi BD. First, let's think about phi CD. Phi CD equals phi CD. We can apply this formula. Change of angle equals G, IP polar moment of inertia, and T, GI feet TL. Polar moment of inertia and twisting moment and length. G, polar moment of inertia, and TCD and length L. We have here, a TCD is given like this one, and length is BD, CD, CD is 40, TCD equals minus 175, length L, CD is 40 millimeter if it is converted to meter, and this one 80 gigapascal Newton per meter squared. Then next one, IP equals 5 over 32, diameter D is given, D exponential 4. Then we can calculate phi CD. Similarly, we can find phi BC. Similarly, GIP, torque BC, and L. Okay. We calculate similarly phi BC value, and finally based on this kind of calculation we can find phi BD. Okay, phi BD is change of angle between B and C. Okay, in this problem we have a powertrain like this one, and torque is acting T1, T2, T3 like this one. T1, T2, T3 is given like this one, and the shaft is attached, mounted the point A and the point E. The shaft of shear modulus of elasticity in the shaft is 80 gigapascal, and we would like to know tau C shear stress in CD, and we would like to know phi BD. Okay, for easier understand, we can draw this kind of a free body diagram, or when you cut there, then we can have this kind of relationship, this kind of free body diagram. Based on this kind of free body diagram, you can calculate TBC, and next, similarly, TCD also, this value can be calculated like this one. Then we can calculate shear modulus of elasticity, BC equals like this one. CD is given like this one. Then we have answer like this one. Next one, finally we would like to know the change of angle between BD. Then firstly we can calculate phi CD, BC. Then we can apply the formula GIP-TL, this formula. Then you can calculate phi CD and phi BC. Then finally you can have answer for this one. In this example, we have a motor and shaft and gear. In the electric motor, we can generate rotational movement. The rotational movement is transmitted to gear. Here we have some values related to driving system. And the motor generates about 30 kilowatt. And Here in the shaft, maximum available shear stress is 42 megapascal, and the rotating speed is 500 rpm, revolution per minute. When you have this kind of data, then we would like to know finally what's required diameter for this shaft. That's our goal. Based on this kind of information, you would like to calculate the diameter of the shaft. In order to find the diameter of the shaft, we can apply this formula. The power relates to RPM and torque. Of course, the RPM is 60 multiplied by frequency. Or this formula can be written to phi ft. Okay, here we would like to apply this formula first because we would like to know torque. If we can calculate torque, then based on torque, we can calculate some relationship between diameter. Okay, tau max equals what? IP TR. We can apply this value. Based on this formula, we can calculate the value torque T. If we know torque T, then we can calculate IP or R relationship. Okay, let's think about this one. P equals 2 phi N is 500 RPM. Torque we don't know, and 60. This value is what? 30 kilowatt. Kilowatt 1000 is converted. Then we can calculate the T value. Okay, we can calculate the T torque. Then let's focus on this one. Tau max equals what? T over 2. IP equals what? 5 over 32 D exponential 4. Then you can change this formula a little bit. D is deleted, just 1, 3, and this one also 16. Okay, then finally 16 T equals 5 D 3. This one is what? Tau max. Then we have D equals 16 T and 5 tau max. When you think about this formula, D exponential 3 equals 16 T 5 tau max. Then 16 T, we know that T 5 and tau max 42 megapascal. 6. Then finally you can calculate the value, diameter of the shaft. Okay, in this problem we calculated finally the diameter of the shaft. When you think about it again, We have a motor, shaft, and gear system, total system. In the motor, we can generate rotational movement. At the same time, some torque is transmitted through shaft to this gear. And some data is given. Transmitting power is 30 kilowatt and maximum available shear stress is 42 megapascal. And rotating RPM equals 500 RPM. And we would like to calculate diameter D. In order to find required diameter D, we use some relationship between torque, RPM, and power. P equals 2 phi nt over 60, and another one, tau max equals TR over IP. When you apply both of them, then first we can calculate torque. And based on this relationship, you can calculate the relationship between diameter and some other data. When you substitute given value to there, and finally you can calculate diameter, required diameter D.